Okay, so let's take a look at question 4, part B from the 2012. So this is the 2012 scholarship paper. And I just completed the video for part A, which was all about DNA and has no relevance to this part. This part is about the amount of carbon dioxide in the atmosphere is increasing due to the combustion of fossil fuels. The concentration of a dissolved gas in a solution is directly proportional to the partial pressure of that gas above the solution. This means that increasing the carbon dioxide in the Earth's atmosphere will increase the amount of dissolved carbon dioxide in the oceans. The concentration of carbonate ions utilized by shell-forming organisms to form calcium carbonate varies with the amount of dissolved CO2. This in turn affects the availability of dissolved calcium ions. And they all lived happily ever after. So, slight sarcasm, that's a lot of text to have to read just to get into a question. And then they follow it with all this information here, which, if you're not comfortable with aqueous systems, is just going to be a complete no-no for you as a question. But if you stay with this question, it actually works out to be a really nice question. I got a genuine kick out of doing it and getting the right answer. So what I need to do is I'm going to use all the information that I can from the text at the beginning as well as from the bullet points to try and build a scaffold to help me approach doing this question. So we'll read on down through the information here. You have an equilibrium equation here for carbon dioxide gas going to aqueous carbon dioxide. You're also given this Henry's law, which isn't taught in level 3 chemistry, but it's one of those ideas where they introduce it in a question and you're supposed to be able to try and figure out how to use it. So Henry's law relates the concentration of aqueous carbon dioxide with the partial pressure of CO2 in the atmosphere to Henry's constant, essentially, Henry's law constant. And then PCO2 is the partial pressure of carbon dioxide in the atmosphere. Henry's law constant for CO2 at 25 degrees Celsius is 3.317 by 10 to the minus 4 moles per liter, and that's times kilopascals per kilopascals to the minus 1. So yeah, again, if you're put off by numbers and units, then this wouldn't be the question for you. The current partial pressure of CO2 in the atmosphere is 0.0397 kilopascals. So that there is your CO2 and your PCO2. That's what that value is right there. Dissolved carbon dioxide reacts with the water to form carbonic acid, which is that. And you're given an equilibrium constant for that equilibrium. Then the carbonic acid, which is a weak acid, further reacts with water to form hydronium ions, and the equilibrium constant for that is given as K2. And then the hydrogen carbonate also reacts with water to form carbonate ions and more hydronium ions. And then you're given the equilibrium constant for that. And then the carbonate will react with calcium in the water to form calcium carbonate, which is a sparingly soluble salt, and you're given the Ks expression for that sparingly soluble salt. And then you're also given the pH of the ocean being 8.0. And here comes the question. Calculate the concentration of calcium ions at the current pH of the ocean using the data given above. So after having read all that, when I first read it, I thought, oh, this is going to be, I don't know where to start. So I just simply started by trying to, as I say, build a scaffold for all this information. So I'm going to take a new page. For you guys, if you want to follow the video, you probably want to have this exam question maybe in your hand as I go through it, because I don't want to keep going over and back from it. But I'll try to show how I build up this little framework. So the amount of carbon dioxide in the atmosphere is increasing due to the combustion of fossil fuels. So the first thing I did, and you may not have time to do this in an exam, but I just want to give a good explanation here. So I just started with a car, and that's your source of additional CO2. So we're talking about global warming as a result of burning too many fossil fuels. So combustion of a fuel, complete combustion, will form CO2 plus water vapor. And we're talking about this stuff enhancing or contributing to the atmospheric levels of gaseous carbon dioxide. Then we go back to the exam question. The concentration of dissolved gas in a solution is directly proportional to the partial pressure of that gas above the solution. So the the partial pressure on this gas, we can just represent that with a large piston. So this is essentially atmospheric pressure. And then from the question, one of the bullet points, they said that the pressure on the gaseous CO2, the PCO2, is equal to 0.0397 kilopascals. That was one of our bullet points. So I'm just symbolizing that with a plunger, putting pressure on the gaseous CO2. If we go back to the question, this means that increasing the carbon dioxide in the Earth's atmosphere will increase the amount of dissolved carbon dioxide in the oceans. Okay, so what we're doing here is we're pushing, there's an equilibrium. They gave us this equation, it's one of the first bullet points. There's an equilibrium between atmospheric CO2 and CO2 which is dissolved in the water. Okay, so that's our schematic. It goes on to say further in the introductory paragraph, so the amount of dissolved carbon dioxide in the oceans will increase. The concentration of carbonate ions utilized by shell-forming organisms to form calcium carbonate varies with the amount of dissolved CO2. This in turn affects the availability of dissolved calcium ions. Okay, so we've used that equation. We've used this partial pressure of CO2. It's in our schematic. The solubility of aqueous CO2 obeys Henry's law. So what I did there was I just introduced Henry's law, because Henry's law is related to how much CO2 aqueous we have. So the CO2 aqueous, according to Henry's law, concentration of that can be found by using the PCO2 and Henry's constant, which is Kh. Henry's constant of Kh is given to us in the exam question as well. Henry's constant of Kh, Henry's law constant is right there, 3.317 by 10 to the minus 4. So if I go back to my scheme, that's Kh there is 3.317 by 10 to the minus 4, and the units are moles per liter times kilo pascal to the minus 1, and that's at a temperature of 25 degrees Celsius. So we've added that to our scheme as well. So what happens next? Well, if we continue on with the exam question, what happens next is, so the solubility of CO2 obeys Henry's law. We've accounted for that in our scheme. We've accounted for the fact that PCO2 is the partial pressure of CO2 in the atmosphere. We've used Henry's law constant there. We've put that in our scheme. The current partial pressure of CO2 in the atmosphere, we've accounted for that. So what happens now? So let's use a different color. So when the carbon dioxide gets into the water, it reacts with the water to form carbonic acid. So we need to include this equation now in our scheme. So the equation now is the carbon dioxide reacts with water. I'm going to use a different color for this. So it reacts with water, liquid, and it's an equilibrium to form carbonic acid H2CO3. Okay, and the K value for that equilibrium constant, which they just call K1, is 1.70 by 10 to the minus 3, which is unitless. Then what happens next is the carbonic acid. If we go back to the question, so we've accounted for the first equation there. The CO2 reacts with water to form carbonic acid. K1 is 1.70 by 10 to the minus 3, so we better include that. We have it, okay, 1.70 by 10 to the minus 3. Back to the exam question. The carbonic acid is a weak acid and further reacts with the water to dissociate and form hydronium ions, and you're given an equilibrium constant for that. So we put that in our scheme. So our H2CO3 carbonic acid plus water liquid, equilibrium established, we form hydrogen carbonate, HCO3 minus, plus hydronium ions. And the K2 for that equilibrium is 2.51 by 10 to the minus 4. And the story continues. Back to the exam question. So we've accounted for that situation. Then the hydrogen carbonate reacts with water to form our carbonate ions plus hydronium ions again, and we have the equilibrium expression for that third equation. So our third situation is the HCO3 minus aqueous plus H2O liquid goes to our carbonate ion, CO3 minus, plus our hydronium ions. And the K3 for that situation is equal to 5.62 by 10 to the minus 11. So that's our story. We have our carbonate ions, and then the final leg of the story is, so we've done that one. The calcium carbonate is a sparingly soluble salt. You're given a Ks for that, and then the pH of 8.10. We'll use that during our calculation. So the question is, calculate the concentration of Ca2 plus ions at the current pH, which is 8.10, using the data above. So this final equation, the fourth equation we need to write, is for the solubility of calcium carbonate. So calcium carbonate, CaCO3 solid, is sparingly soluble, therefore it's in equilibrium with its two constituent ions, which are calcium, Ca2 plus, and then our carbonate. So our carbonate is going to contribute to that concentration, and the Ks value for that was equal to 4.8 by 10 to the minus 9. So that's our scheme. That's how I approached doing this question. Was I laid down all the information that in a coherent fashion, and it flows really nicely. So what we have to do now is we basically have to work through each of these equations. We start using Henry's law, Henry's equation to find the concentration of CO2, and then we'll work from that to find the concentration of hydrogen or carbonic acid. And then once we have the concentration of the carbonic acid, we'll work out the hydrogen carbonate, then the carbonate itself, and then finally use this final equation, number 4, to work out the concentration of Ca2 plus. So I'm just going to number these equations as well so we can follow them. So this is equation number 1, and this is equation number 2, equation number 3, and then this is equation number 4. So, okay, so I've just laid out a new page, just to go through each of these steps. But the first step is to figure out the concentration of aqueous CO2 using Henry's formula there, and equation number 1. So I've laid out this page. So step 1 is to find the concentration of aqueous CO2 using Henry's law. Henry's law is as follows. So the concentration of CO2 aqueous over CO2 partial pressure on Henry's constant. So therefore the concentration of CO2 aqueous which is equal to 3.317 by 10 to the minus 4 moles per liter times kilopascals to the minus 1 multiplied by 0.0397 kilopascals, which was the partial pressure of CO2 given in the question, and that gives a value of 1.32 by 10 to the minus 5 moles per liter. So that's our concentration of CO2. So then what I'm going to do is I'm just going to return back to the original scheme. So our concentration of CO2, let's put it in a nice color which stands out, is now equal to 1.32 by 10 to the minus 5 moles per liter. So that was the first step. The second step now is we use that concentration for CO2 and equation number 1 to work out a concentration for our carbonic acid. So here we go, step 2. Step 2 is to find the concentration of carbonic acid using carbon dioxide aqueous and equation number 1. So for this situation, we better write down the equation. It's so it's CO2 aqueous plus H2O liquid, equilibrium going to our carbonic acid. So there's an assumption we need to make here. Assume that the concentration of H2O is constant. And if you think about it, it's a huge ocean. There's very little dissolution we can do to seriously affect the concentration of the HO2. So assume the concentration of H2O is constant, and therefore K1 is equal to the concentration of products over reactants. So this is simply how to write an equilibrium expression from level 2. So you put the concentration of the products over the concentration of the reactants. So in this case, K1 is equal to the concentration of H2CO3 over the concentration of our CO2 aqueous, and the water is eliminated from the expression based on our assumption here. So K1 was given to us originally, and therefore our calculation is 1.70 by 10 to the minus 3. That was the K1 value, multiplied by our concentration for CO2, which we just found to be 1.32 by 10 to the minus 5 moles per liter, and that gives us a concentration of 2.24 by 10 to the minus 8 moles per liter for the concentration of our carbonic acid. So if we revert back to our original page here, use our pink, and therefore the concentration of our carbonic acid we just found is 2.24 by 10 to the minus 8 moles per liter. So we're moving well now. Once you get into this question, you realize that you just flow down through it. So we have our concentration of carbonic acid. The third step now is to find the concentration of the hydrogen carbonate using equation number 2. So we go back here, step number 3, find the concentration of our hydrogen carbonate using our carbonic acid. Our carbonic acid concentration we just found to be 2.24 by 10 to the minus 8 moles per liter. So we write down this equation number 2, and equation number 2 is, let's just use a different color because this is becoming all one big block of green, so let's use red. So equation number 2 was H2CO3 aqueous, equilibrium established, CO3 plus H3O plus. Okay, so step 3, we're trying to find the concentration of our hydrogen carbonate here. I've written out equation 2 because that's what we're using to work with. K2, the equilibrium expression, again, concentration of the products. Ignore the water based on the assumption we made at the beginning there. For all these equations, we're assuming the concentration of water is constant. So the value of K2 was, back at the beginning, the value of K2 was 2.51 by 10 to the minus 4. The concentration of H2CO3, we just found the concentration of H2CO3, and that was equal to 2.24. That's equal to 2.24 by 10 to the minus 8 moles per liter. So the only concentration we need to work out now is the H3O plus, and that will allow us to get the HCO3 minus. So how do we find this? Well, if you remember at the bottom of the question, they said the pH was equal to 8.10. So therefore the concentration of H3O plus is simply 10 to the minus pH, which is equal to 7.94 by 10 to the minus 9 moles per liter. Okay, so if you plug all those numbers in, you work out that the concentration of HCO3 minus is equal to 7.08 by 10 to the minus 4 moles per liter. So that's your H3O plus concentration that went in there. So you put all those numbers in and rearrange the expression, and you get a value for your hydrogen carbonate. So it's 7.08 by 10 to the minus 4. And the question continues. So we've just worked out concentration for hydrogen carbonate of 7.08 by 10 to the minus 4 moles per liter. So the next step in the question, finally we're getting down to what we need to know, is we need to work out the concentration of our carbonate ions. So we go back here again. We're going to get a new page for this. So step 4 of the question, we want to find the concentration of carbonate now using the concentration of hydrogen carbonate, which we just established, and that was 7.08 by 10 to the minus 4 moles per liter. Using our equation number 3 here, which was hydrogen carbonate plus water, breaks up into carbonate ions plus hydronium ions, and the K3 for that is 5.62 by 10 to the minus 11. So K3, our equilibrium expression, is equal to the products times each other over the concentration of reactant. Again, we're assuming that the concentration of water is constant, so we don't include it in the expression. The concentration of this is still 7.94 by 10 to the minus 9 moles per liter, like we just worked out in step number 3. So the pH of the solution is assumed to be still 8.10. The concentration we just said of the hydrogen carbonate was 7.08 by 10 to the minus 4 moles per liter. And the K3 value is right there. So if you put all those numbers in, you get a concentration of carbonate ions equal to 5.01 by 10 to the minus 6 moles per liter. So we're nearly there with the question. We add that to our page here. So our concentration of carbonate ions is 5.01 by 10 to the minus 6 moles per liter. And then the final step in the question, step number 5 here, find the concentration of calcium ions using your carbonate ion concentration and equation number 4. So the equation number 4 is essentially for we wrote this already, it's for the sparingly soluble dissolution of calcium carbonate solid into its component ions, which are calcium plus carbonate ions. I don't know why I put concentration brackets on there, get rid of those. So our expression for that, the Ks expression, is simply the concentration of the products times each other. We're assuming that the concentration of the calcium carbonate is unchanging. That's one for a saturated solution. But there's an assumption there that the concentration of calcium carbonate is unchanging. So therefore you can write your Ks expression like that. And then simply all you have to do is the Ks over the concentration of your carbonate ions will equal to the concentration of your calcium at the pH of 8.0, and that's equal to 4, well, the Ks is 4.8 by 10 to the minus 9. That was given to you in the question, and we just worked out the concentration of our carbonate ions as 5.01 by 10 to the minus 6 moles per liter. So it gives you a final answer of 9.58 by 10 to the minus 4 moles per liter, and that's at a pH in the ocean of 8.1. So I was really chuffed when I got that answer and it matched up with the NCEA answer. You would have really had to back yourself doing that question in an exam paper to go through all those steps, but the good thing is you'll pick up attempt marks along the way, because a lot of what I was writing and knew was along the right track, even if the calculations weren't giving the exact same numbers. So happy with that question. That's question 4 part B from the 2012 scholarship paper.